15 billion miles from Earth, in the absolute darkness of interstellar space, a spacecraft the size of a small car is dying. It has been traveling for nearly 50 years. It is the farthest human-made object in existence. Nothing we have ever built has gone this far. Nothing we have ever constructed has survived this long in conditions this hostile. And on February 27, 2026, this dying spacecraft sent back a transmission that made the engineers monitoring it go silent. The data showed something they had feared but hoped they would never see. Voyager 1's power levels had dropped unexpectedly during a routine maneuver. The spacecraft was dangerously close to triggering its own emergency shutdown system. If that system activated, Voyager 1 would go into a protective coma from which recovery would be uncertain at best and impossible at worst. Humanity's most distant explorer, the probe that carries a golden record containing the sounds and images of our civilization, was on the edge of going permanently silent. 15 billion miles from home. Alone in the void between stars. With no possibility of rescue. But what frightened scientists was not merely the power drop. It was what Voyager 1 had been detecting in the months before the crisis. Strange readings from interstellar space. Unexpected increases in plasma density and magnetic field intensity. Data patterns that did not match any known cosmic phenomenon. Something in the space between stars was not behaving the way our models predicted. And the spacecraft that discovered this anomaly was now fighting for its own survival. If you want to understand what Voyager 1 found in the darkness between stars and why scientists are racing against time to keep it alive long enough to tell us more, hit that like button and subscribe right now. This story will change how you think about our place in the cosmos. Let's begin. To understand why Voyager 1's recent transmissions alarmed the scientific community, you need to understand what Voyager 1 actually is and why losing it would represent a loss unlike anything in the history of space exploration. Because Voyager 1 is not just a spacecraft. It is a time capsule, a scientific instrument, and a philosophical statement about human ambition, all compressed into a machine weighing less than a ton, hurtling through the void at approximately 38,000 miles per hour with no way to slow down, no way to turn around, and no way to come home. Voyager 1 launched on September 5, 1977, from Cape Canaveral, Florida, atop a Titan IIE Centaur rocket. It was one of a pair of identical spacecraft. Its twin, Voyager 2, had launched 16 days earlier on August 20. The original mission was modest by cosmic standards. The two Voyagers were designed to take advantage of a rare planetary alignment that occurs once every 176 years, an arrangement that placed Jupiter, Saturn, Uranus, and Neptune on the same side of the Sun, allowing a single spacecraft to visit multiple outer planets using gravitational assists to slingshot from one world to the next. The primary mission was budgeted for 4 years. Voyager 1 would fly past Jupiter and Saturn. Voyager 2 would follow a different trajectory, visiting all 4 gas giants. After the planetary encounters, the mission would end. The spacecraft would drift silently into the outer solar system, their instruments powered down, their antennas slowly losing alignment with Earth. They would become cosmic debris. Artifacts of a brief period of human curiosity, tumbling through the darkness until the heat death of the universe or until some unimaginable future event destroyed them. That was the plan. The universe had other ideas. Voyager 1 arrived at Jupiter in March 1979 and immediately began rewriting textbooks. It captured the first detailed images of Jupiter's turbulent atmosphere, revealing storm systems larger than Earth that had been raging for centuries. It discovered active volcanoes on Jupiter's moon Io, the first confirmed volcanic activity ever observed on another world. The images showed plumes of sulfur and sulfur dioxide erupting hundreds of kilometers above Io's surface, a discovery so unexpected that it forced an immediate revision of planetary science models. Moons were not supposed to be volcanically active. Io was supposed to be a cold, dead rock. Instead, it was the most volcanically active body in the entire solar system, powered by tidal heating from Jupiter's enormous gravitational field. Voyager 1 then swung past Saturn in November 1980, providing the first detailed look at the planet's ring system. The rings, which appeared smooth and uniform through ground-based telescopes, were revealed to be extraordinarily complex structures composed of thousands of individual ringlets separated by gaps of varying widths. Voyager discovered shepherding moons that maintained the ring's structure through gravitational interactions. It observed spokes in the rings, transient dark features that rotated with the planet's magnetic field rather than with the orbital motion of the ring particles, a phenomenon that remains incompletely understood to this day. It flew close to Titan, Saturn's largest moon, and discovered that Titan possessed a dense nitrogen atmosphere thicker than Earth's, the only moon in the solar system known to have a substantial atmosphere. The encounter was so scientifically rich that NASA chose to redirect Voyager 1's trajectory for a close Titan flyby, sacrificing the opportunity to continue on to Uranus and Neptune. That decision would be left to Voyager 2 alone. After Saturn, Voyager 1 entered the long cruise phase of its mission. It climbed steadily away from the plane of the solar system, heading generally northward relative to the ecliptic plane. Year after year, it moved farther from the Sun. The distance grew. The signal weakened. The power slowly declined. Most of its instruments were shut down one by one to conserve energy. But the spacecraft kept flying. And it kept transmitting. A faint whisper of radio waves, traveling at the speed of light across billions of miles of empty space, arriving at Earth's deep space network antennas as a signal so weak that the power received was 20 billion times less than the power of a digital watch battery. In February 1990, at the suggestion of astronomer Carl Sagan, Voyager 1 turned its camera back toward the inner solar system one final time and captured a series of images that would become one of the most famous photographs in human history. In one of those images, Earth appeared as a tiny dot, less than a single pixel in size, suspended in a beam of scattered sunlight. Sagan called it the pale blue dot. He wrote that the image showed everything we had ever known, every human being who had ever lived, every war ever fought, every love story ever told, every act of kindness and every act of cruelty, all of it contained on a mote of dust suspended in a sunbeam. The image was taken from approximately 3.7 billion miles away. Today, Voyager 1 is more than 4 times farther than that. After the pale blue dot photograph, Voyager 1's cameras were permanently shut down. There was nothing ahead to photograph. The spacecraft was heading into the outer reaches of the solar system, regions so dark and so empty that no image could capture anything meaningful. But other instruments remained active. The magnetometer, which measures magnetic fields. The cosmic ray subsystem, which detects high-energy particles. The plasma wave subsystem, which listens to vibrations in charged particles. The low-energy charged particles experiment, which measures ions and electrons. These instruments continued to collect data about the environment through which Voyager 1 was traveling. And what they detected, over the following decades, told a story that no one had anticipated. As Voyager 1 moved beyond the orbits of the known planets, it entered a region called the heliosheath, the outermost layer of the heliosphere. The heliosphere is a vast bubble of charged particles and magnetic fields generated by the sun's solar wind. This bubble extends far beyond the planets, creating a protective cocoon that partially shields the solar system from the harsh radiation environment of interstellar space. The boundary of this bubble, called the heliopause, marks the point where the sun's influence ends and interstellar space begins. No spacecraft had ever reached this boundary. No instrument had ever measured the transition from solar dominion to interstellar freedom. Voyager 1 was about to become the first. The approach to the heliopause was not smooth. In 2004, Voyager 1 crossed a boundary called the termination shock, the point where the solar wind abruptly slows from supersonic to subsonic speeds as it encounters the pressure of the interstellar medium. The termination shock was closer to the Sun than many models had predicted, suggesting that the heliosphere was being compressed by external pressure from the interstellar environment. The data was the first direct evidence that the space between stars was not empty or passive. It was pushing back against the Sun's influence. Beyond the termination shock, Voyager 1 entered the heliosheath proper, a turbulent region where the slowed solar wind piles up against the approaching interstellar medium. The environment was chaotic. Magnetic fields fluctuated wildly. Particle densities varied unpredictably. The instruments recorded data that did not match any of the models that had been developed to predict what this region would look like. The heliosheath was stranger, more dynamic, and more complex than anyone had expected. Then, on August 25, 2012, something remarkable happened. Voyager 1 crossed the heliopause. It left the heliosphere entirely and entered interstellar space. The transition was marked by a sharp and dramatic change in the particle environment. The density of solar particles dropped precipitously while the density of galactic cosmic rays surged. The magnetic field changed direction, aligning with the interstellar field rather than the solar field. Voyager 1 had done something that no human artifact had ever done before. It had left the solar system's protective bubble and entered the space between stars. The interstellar medium that Voyager 1 encountered was not what scientists expected. Models had predicted a relatively uniform environment, a thin soup of hydrogen atoms and cosmic ray particles permeated by a steady magnetic field. What Voyager actually measured was far more complex. The magnetic field in the immediate vicinity beyond the heliopause was stronger than predicted and oriented differently than models suggested. The plasma density was higher than expected. And the transition between solar and interstellar environments was sharper and more abrupt than the gradual blending that most models had predicted. Then, in 2020, Voyager 1's instruments detected something genuinely puzzling. The magnetometer registered an abrupt jump in the intensity of magnetic fields embedded in the interstellar plasma. Simultaneously, the plasma wave detector measured a corresponding rise in plasma density. The readings suggested that Voyager 1 had encountered a pressure front or density wave moving through interstellar space. Scientists initially attributed these anomalies to shock waves generated when bursts of solar activity, coronal mass ejections and solar flares, slammed into the heliopause and sent pressure waves reverberating outward into the interstellar medium. This explanation made physical sense. The Sun periodically releases enormous bursts of energy that propagate outward through the solar wind. When these bursts reach the heliopause, they compress the boundary and generate waves that travel into interstellar space like ripples spreading across a pond. But as Voyager 1 continued to travel deeper into interstellar space, the anomalies did not stop. They continued. They changed character. In some cases, the plasma density increases persisted for months rather than the weeks that shockwave models predicted. The magnetic field fluctuations exhibited patterns that did not match the expected signatures of solar-driven disturbances. Something in the interstellar medium was generating effects that could not be fully explained by solar activity alone. The plasma wave subsystem detected a persistent low-frequency hum in the interstellar medium. This hum, first reported in 2021, represented a continuous background vibration in the plasma surrounding Voyager 1. Unlike the transient bursts associated with solar shock waves, the hum was steady, ongoing, and consistent. It suggested that the interstellar medium possesses a baseline level of activity that exists independently of solar influence. The interstellar space that had been imagined as a quiet, static void was instead a dynamic environment with its own internal processes and energy sources. Scientists at Cornell University, Iowa State University, and other institutions analyzed the plasma wave data and concluded that the hum corresponded to a narrow frequency band consistent with the thermal vibration of interstellar plasma at very low densities. This was, in one sense, unremarkable. Plasma at any temperature vibrates. But the steadiness of the signal, its persistence across months and years of observation, and its resistance to variation suggested that the interstellar medium in Voyager 1's vicinity was remarkably uniform over large distances. The hum was the heartbeat of the space between stars. Quiet, steady, ancient, and unceasing. But in 2025 and into early 2026, the data took another unexpected turn. The readings from Voyager 1's remaining instruments began showing variations that did not fit cleanly into either the solar shockwave model or the steady background hum model. Magnetic field intensities fluctuated in patterns that appeared quasi-periodic, rising and falling over timescales of weeks to months in ways that did not correlate with known solar activity cycles. Plasma density measurements showed localized increases that suggested Voyager 1 was passing through regions of enhanced density within the interstellar medium, regions that had not been predicted by any existing model of the local interstellar environment. Some researchers proposed that Voyager 1 was encountering the boundary of a previously unknown structure in the interstellar medium, perhaps a cloud of denser material, a region compressed by ancient supernova remnants, or a magnetic filament threading through the space between stars. The local interstellar medium is not perfectly uniform. It is structured by the remnants of stellar explosions that occurred millions of years ago, by the magnetic fields generated by the galaxy's differential rotation, and by turbulence arising from the interaction between different regions of varying density and temperature. Voyager may first have been encountering one of these structures for the first time, providing direct in situ measurements of a feature that had previously been inferred only through indirect astronomical observations. Then came the crisis of February 27, 2026. During a routine planned roll maneuver, a standard procedure where the spacecraft rotates to calibrate its instruments, Voyager 1's power levels dropped unexpectedly. The drop was small in absolute terms but enormous relative to the razor-thin margins within which the spacecraft operates. After nearly 50 years in space, Voyager 1's 3 radioisotope thermoelectric generators produce less than half their original power output. The generators convert heat from decaying plutonium-238 into electricity, but the plutonium decays at a fixed rate, and the thermoelectric elements that convert heat to electricity degrade over time. The spacecraft loses approximately 4 watts of power every year. In 2026, the total available power is critically low. Every instrument, every heater, every system aboard draws from this diminishing supply. The margins between operational power and the undervoltage threshold that triggers the spacecraft's emergency fault protection system are measured in single-digit watts. The February power drop brought Voyager 1 dangerously close to that threshold. If the undervoltage protection system had triggered, it would have automatically shut down non-essential systems to protect the spacecraft. Recovery from such an event, at a distance where commands take 23 hours to arrive and confirmation takes another 23 hours to return, would be a nerve-wracking process lasting weeks with no guarantee of success. The Voyager team at JPL needed to act before the spacecraft acted for itself. On April 17, 2026, NASA sent the command to shut down the low-energy charged particles experiment, an instrument that had been operating almost continuously for 49 years. The LECP measured ions, electrons, and cosmic rays in the interstellar environment. It had provided critical data about the structure of the space beyond the heliosphere, detecting the pressure fronts and density variations that had puzzled and fascinated scientists. Shutting it down was not a decision made lightly. It had been planned for years as part of a carefully determined sequence of instrument shutdowns designed to extend the mission as long as physically possible. Of the 10 original instrument sets aboard Voyager 1, 7 had already been shut down over the preceding decades. The LECP was 8th on the list. Its shutdown was expected to provide approximately 1 additional year of operational life. But the LECP shutdown was not the end of the story. It was the prelude to something far more ambitious and far more dangerous. The Voyager engineering team has been developing a radical power management strategy they call the Big Bang. The concept involves simultaneously swapping out multiple powered components for lower power alternatives in a single coordinated maneuver. Instead of the incremental approach of shutting down one system at a time, the Big Bang would reorganize the spacecraft's entire power architecture in one bold move, replacing power-hungry components with more efficient alternatives to free up enough energy to keep the remaining instruments operating and the spacecraft warm enough to survive. The Big Bang strategy will be tested first on Voyager 2, which has slightly more available power and is closer to Earth, making it a safer test subject. The tests are scheduled for May and June of 2026. If successful, the same approach will be applied to Voyager 1 no earlier than July 2026. If the Big Bang works as planned, it could extend Voyager 1's operational lifetime by several additional years. It might even free up enough power to reactivate the LECP instrument, restoring the ability to measure the charged particles in the interstellar medium that had been generating such puzzling data. A small motor within the LECP has been deliberately left running at a power cost of just half a watt, specifically to preserve the possibility of restarting the instrument in the future. The stakes could not be higher. Voyager 1 is the only spacecraft in interstellar space capable of making these measurements. Voyager 2 crossed the heliopause in 2018 but is traveling in a different direction through a different region of interstellar space. The two spacecraft together provide the only direct sampling of the interstellar medium that humanity has ever achieved or is likely to achieve for decades to come. No other mission currently planned or under development will reach interstellar space before the 2070s at the earliest, and most estimates place the next interstellar probe decades beyond that. If Voyager 1 goes silent, the data it was collecting will be irreplaceable. The anomalies it was investigating will remain unexplained. The structures it was beginning to reveal in the interstellar medium will remain unmapped. A window into the space between stars will close, and it may not reopen within the lifetime of anyone currently alive. This is what makes the current situation so compelling and so urgent. Voyager 1 is not merely running low on power. It is running low on power at precisely the moment when it is detecting phenomena that no one predicted and no one fully understands. The interstellar medium is not the quiet, uniform void that models suggested. It is structured, dynamic, and full of features that Voyager 1 was only beginning to characterize when its power crisis forced the shutdown of key instruments. The spacecraft is caught between two imperatives: the need to conserve power to survive and the need to keep instruments running to understand what it is flying through. Every day, Voyager 1 travels approximately 900,000 miles deeper into interstellar space. Every day, it moves further from the Sun, further from Earth, further from any possibility of repair or rescue. Every day, its power diminishes by an imperceptible fraction. Every day, the margin between operation and silence grows thinner. And every day, the data it sends back, traveling at the speed of light across 15 billion miles of void, arriving at Earth's antennas 23 hours after transmission, tells us something about a region of space that no human instrument has ever measured before. Something we cannot learn any other way. Something that, once lost, may be lost forever. The philosophical dimension of Voyager 1's situation deserves attention because it transcends the technical details of power management and instrument shutdowns. Voyager 1 carries, bolted to its side, a golden phonograph record containing sounds and images selected to represent the diversity of life and culture on Earth. The record includes greetings in 55 languages, samples of music ranging from Bach to Chuck Berry, sounds of wind, thunder, birds, whales, and a human heartbeat. It contains 116 images depicting life on Earth, from mathematical definitions to photographs of people, landscapes, and architecture. The record was designed by a committee chaired by Carl Sagan as a message to any extraterrestrial intelligence that might someday encounter the spacecraft. The golden record is humanity's message in a bottle, cast into the cosmic ocean with no expectation that it will ever be found. It is simultaneously the most optimistic and the most futile gesture our species has ever made. Optimistic because it assumes that intelligence and curiosity are not unique to Earth, that somewhere in the vast interstellar medium there might exist beings capable of finding the record, decoding its contents, and understanding its meaning. Futile because the distances involved are so enormous and the probability of encounter so vanishingly small that the record will almost certainly drift through the void for billions of years without ever being found by anyone. Yet the record endures. It is attached to a spacecraft that is still functioning, still transmitting, still conducting science nearly half a century after launch. In a universe governed by entropy, where every organized structure eventually decays, Voyager 1's continued operation is a small but genuine act of defiance against the tendency of all things to fall apart. The spacecraft was designed for a 4-year mission. It has operated for nearly 50 years. It has crossed boundaries that were not even theoretically defined when it launched. It has entered a realm of space that no human artifact was ever expected to reach. And it continues to send back data that challenges our understanding of the cosmos. The engineers at JPL who manage the Voyager missions are among the most experienced deep space operators in the world. Many of them have spent their entire careers working on the Voyager project. They understand the spacecraft's systems with an intimacy that comes from decades of continuous interaction. They know every quirk, every vulnerability, every creative workaround that has been devised over the years to keep the aging probe functioning. When they describe the Big Bang maneuver as risky, the word carries weight. These are not people who use that term casually. The Big Bang will require simultaneous changes to multiple spacecraft systems at a distance where each command takes 23 hours to arrive. If something goes wrong during the maneuver, the team will not know for nearly a full day. And by the time they learn of the problem, another day will pass before any corrective command can reach the spacecraft. 46 hours of uncertainty during a procedure that could determine whether Voyager 1 continues to function or falls silent forever. Voyager 1 currently has 2 remaining operational science instruments. The magnetometer, which measures the magnetic fields that permeate interstellar space. And the plasma wave subsystem, which detects vibrations in charged particles and has been responsible for detecting the persistent interstellar hum that has fascinated scientists. These 2 instruments continue to return data from a region of space that no other human-made device has ever explored. Every measurement they make is unique. Every data point is irreplaceable. Every transmission that arrives at Earth's antennas after its 23-hour journey across the void represents something that cannot be obtained any other way. The plasma wave subsystem is particularly significant because it provides the most direct measurement of plasma density in the interstellar medium. This density is a fundamental property of the space between stars, and it varies in ways that reveal the structure and dynamics of the local interstellar environment. The persistent hum detected by the PWS represents the baseline thermal activity of the interstellar plasma, a measurement that was only possible because Voyager 1 traveled far enough from the Sun for solar noise to fall below the threshold of the interstellar signal. This measurement constrains models of the local interstellar medium in ways that remote astronomical observations cannot. The magnetometer data is equally valuable. The magnetic field in the interstellar medium is generated by the differential rotation of the Milky Way galaxy and by the remnants of ancient supernova explosions that stirred and compressed the interstellar gas. The field is weak by terrestrial standards but has enormous influence on the behavior of charged particles, the propagation of cosmic rays, and the structure of the heliosphere's outer boundary. Voyager 1's magnetometer provides the only direct, in situ measurements of this field from within the interstellar medium. Remote observations from Earth can infer the field's properties through indirect techniques like Faraday rotation of polarized radio signals from distant pulsars, but these methods provide averaged values over enormous distances. Voyager 1 measures the field at a single point, revealing local variations and structures that averaged observations would smooth away. Together, these 2 instruments tell us something profound about the environment that surrounds our solar system. They reveal that interstellar space is not the featureless void that earlier generations imagined. It is a structured, dynamic medium with its own internal processes, its own energy sources, and its own variations in density, temperature, and magnetic field strength. The space between stars is not empty. It is an environment, as real and as complex as any planetary atmosphere, governed by physical processes that operate on scales of light years and timescales of millions of years. And Voyager 1 is our only direct connection to that environment. Our only sensor in the interstellar ocean. Our only ambassador to the space between stars. If it falls silent, that connection is severed. The data stops. The measurements end. The anomalies remain unexplained. The structures remain unmapped. And the interstellar medium returns to being something we can only study from afar, inferring its properties through indirect observations rather than measuring them directly. This is why the February 2026 power drop scared scientists. Not because a spacecraft losing power is unusual. All spacecraft eventually run out of power. But because this spacecraft, at this moment, in this location, is providing data that cannot be obtained any other way. Losing Voyager 1 now would be like losing the only thermometer in the ocean, the only seismometer on a geologically active planet, the only microphone in a room where someone is speaking words never before heard. The information loss would be permanent and irreplaceable. The Voyager team is fighting to prevent that loss. The Big Bang maneuver, if successful, could extend Voyager 1's operational lifetime by years. It could free enough power to reactivate the LECP instrument. It could allow Voyager 1 to continue mapping the interstellar medium as it travels deeper into the space between stars. It could provide answers to the anomalies that the spacecraft has detected. It could reveal whether the density variations and magnetic field fluctuations represent local structures in the interstellar medium or something more fundamental about the environment that surrounds our solar system. But the Big Bang is not guaranteed to work. The spacecraft is old. Its systems have degraded over nearly 50 years of exposure to cosmic radiation, extreme temperatures, and the relentless vibration of its own mechanisms. Components that have functioned flawlessly for decades might fail when asked to change their operational parameters. Connections that have remained stable might break under the stress of reconfiguration. The risk is real. The consequences of failure are permanent. And the team at JPL knows this better than anyone. Voyager 1 is currently approximately 15.1 billion miles from Earth. At that distance, the spacecraft's radio signal, traveling at the speed of light, takes approximately 23 hours to reach Earth. The signal is extraordinarily weak. By the time it arrives at the Deep Space Network's 70-meter dish antennas in California, Spain, and Australia, the power of the received signal is approximately 20 billion times weaker than the power produced by a typical digital watch battery. Extracting meaningful data from this whisper requires sophisticated signal processing and enormous antenna surfaces. The spacecraft travels at approximately 38,000 miles per hour relative to the Sun. It will reach one light day from Earth in 2026, a milestone that underscores both how far it has traveled and how much further the stars remain. Alpha Centauri, the nearest star system, is approximately 4.37 light-years away. At Voyager 1's current speed, reaching Alpha Centauri would require approximately 73,000 years. Voyager 1 is not heading toward Alpha Centauri. Its trajectory will carry it past a star called AC plus 793888 in the constellation Camelopardalis in approximately 40,000 years, passing within about 1.6 light-years. It will not stop. It carries no braking mechanism. It will drift past that star and continue into the galaxy, a silent artifact carrying a golden record that no one will play, traveling through a void that stretches in every direction without end. Unless the Big Bang works. Unless the power holds. Unless the instruments continue to function. Unless the data continues to flow. In that case, for a few more precious years, Voyager 1 will continue to be our eyes and ears in the interstellar medium. It will continue to measure the magnetic fields and plasma densities and charged particle fluxes that reveal the structure of the space between stars. It will continue to detect anomalies that challenge our models and deepen our understanding. It will continue to send back whispers from the void that tell us something true about the cosmos we inhabit. Voyager 1 is dying. This is not metaphor. It is physics. The plutonium in its generators decays at a fixed, immutable rate. The power output decreases by 4 watts every year. No engineering brilliance can alter the half-life of an isotope. No software update can regenerate depleted nuclear fuel. The spacecraft's death is written into the laws of nuclear physics, as certain and as irreversible as the expansion of the universe itself. The only question is how long the team at JPL can delay the inevitable through ingenuity, creativity, and an intimate understanding of a machine that has outlived every expectation. But until that final silence comes, Voyager 1 continues to speak. It speaks in the language of magnetic field measurements and plasma wave frequencies and charged particle counts. It speaks across 15 billion miles of void. It speaks to antennas pointed at a patch of sky where nothing is visible to the naked eye. It speaks in whispers so faint that only the most sensitive receivers on Earth can detect them. And what it says is this: the space between stars is not empty. It is not silent. It is not featureless. It is an environment as real and as complex as any place in the solar system. And we are only beginning to understand it. The golden record bolted to Voyager 1's side contains a message from humanity to the cosmos. Greetings in 55 languages. Music from every continent. Images of our world and our species. The sounds of wind and rain and laughter and heartbeats. It is a message of hope and curiosity, sent outward into the unknown with no expectation of reply. But Voyager 1 itself is sending a different message. Not outward to the cosmos, but inward to us. It is telling us that the universe is larger and stranger and more complex than we imagined. That the space we thought was empty is full. That the void we thought was silent has a voice. And that our capacity to explore, to discover, to understand, depends on machines and people and institutions that are themselves fragile, temporary, and mortal. Voyager 1 will eventually go silent. The power will run out. The transmitter will fail. The last data point will be received and the antennas will hear nothing more. The spacecraft will continue to travel through interstellar space, a frozen relic carrying a golden record that will outlast every civilization that currently exists on Earth. It will drift through the galaxy for millions of years. Billions, perhaps. Long after the sun has swollen into a red giant and consumed the inner planets. Long after the Milky Way has merged with Andromeda. Long after every star currently burning has exhausted its fuel and faded to darkness. Voyager 1 will still be out there. Silent. Cold. Carrying the sounds of a world that no longer exists. But right now, today, at this moment, it is still alive. It is still transmitting. It is still teaching us about the cosmos. And the engineers at JPL are still fighting to keep it going, one watt at a time, one instrument at a time, one day at a time. Humanity's most distant explorer has not yet spoken its last word. The question is what that word will be. And whether we will be listening when it comes. So here is my question for you in the comments. Voyager 1 has been traveling for nearly 50 years and is now 15 billion miles from home. It carries a golden record containing the sounds and images of our civilization, a message to anyone who might find it in the distant future. If you could add one thing to that golden record, one sound, one image, one message that represents humanity, what would it be? And here is a deeper question. When Voyager 1 finally goes silent, when the last transmission arrives at Earth and the antennas hear nothing more, will that moment represent a failure or a triumph? Did we lose a spacecraft, or did we prove that human curiosity can reach beyond any boundary that the universe places in front of us? Let me know your thoughts below. I am genuinely curious about your perspective. Let us discuss it together.